When we write things like f of x equals 3x plus 1, what we mean is we're describing a procedure named f that we can put numbers into and get various numbers out of. For example, if f of x is 3x plus 1, I take 0 and feed it through the f procedure. The symbol that we use is f of 0, which would work out to be 1 in this case. Likewise, feed 1 through the f procedure to get f of 1, which works out to be 4, and likewise for 1/3. We're used to thinking that we can plug any number into the function that we want with some provisos. For example, we can't do the principal square root of a negative number or the natural logarithm of 0. But other than that kind of thing, we're used to thinking of entire intervals of numbers that we could put into such a thing. If I make a picture with the inputs on the horizontal axis and the outputs on the vertical axis, and then draw in these points that we've figured out, I get this point, this one, and this one. Of course, since I'm free to make the input anything I want, I could plot many other points, as many as I would care to do, and I would get the usual picture out of it. When we want to speak of limits of such things, like the limit as x approaches 4 of f of x, all that I need to have is that the function makes sense every place close to x equal 4, although it doesn't need to make sense right at x equal 4. If all of those function values begin to resemble a certain number as I make x closer to but never equal to 4, then we call that number the limit of the function. Some functions are very nice. Sometimes the limit is just plug the number in. Those are the continuous functions. Formally speaking, a sequence is going to be a function, but it's a new kind of function. The inputs are going to be integers, positive integers usually, 1, 2, 3, and so on. Sometimes it's convenient to start counting at 0, so I might have 0 or 1 or 2 or 3 and so on, but not something like 1.47 or 2.5 or pi. The kind of functions that we've talked about previously, typically we call the name of the function f or g or some other such letter. We call the function values f of x, g of x, and so on. If I wanted to be picky about it, these new things, these sequences, I should pick a letter to represent the name of the function. Commonly seen are letters like A and B down towards the beginning of the alphabet. I really should write A of n and B of n, where n is an integer. But what people do is they write A with a subscript of n, B subscript n. People will often just pronounce those as AN, BN, sometimes a number n for emphasis, sometimes a sub n. So these are analogous to those. As an example of this kind of thing, think about a sub n equals 3n plus 2 over 2n plus 4, where n can be positive whole numbers from 1 on up. If I put n equal 1, 2, or 3 into this formula, I can figure out the corresponding function value, a1, a2, a3, and so on and so forth. If I graph horizontally the value of n and vertically the an, I can plot these 3 points. These are 3 points on the graph of the a function, the sequence function, and we need to get something very clear here. Mostly, I can't even think about the kind of calculus stuff that we've done in the past. if I try to think about the limit as n tends to 2 of an, that makes no sense. For the limit to exist, the function value would have to exist for all inputs that are close to but not equal to 2, and that's not the case. I have a function value at n equal 2, but I don't have one at 1.9 or 1.5 or 2.01. I just have the single function value. So this doesn't even make any sense in this context. I could think of making up some nicer curve that passes through those points and think about the limit of it. This would open the door to limits, but there's still a problem. I could draw in something like this, or I could draw in other things as well. So even though I might be able to make some sort of sense out of limits, if I start thinking about slopes of tangent lines, clearly there's no chance of that kind of thing. We will be able to do some calculus in a certain sense, but we're going to have to think carefully about this. The kind of limit that we're going to talk about, though, has to do with the index, or the number that I'm feeding into the a function. Taking limits as n approaches 2.4 doesn't make any sense, but I can think about what happens when n becomes very big. So if you look at n equals 110,000 and a million, and look at the corresponding a numbers, you start off at 0.8 and then an infinite string of threes, 1.3 repeating, 1.48039, 1.4998, and 1.499998. Looking at these numbers, we begin to suspect something. I suspect that if I make the index, the n, big enough, then the a sub n's will become as close to 1.5 as I care to make them. Speaking a little bit more formally, given any positive number epsilon, there's going to be an index capital N, so that if the index on the a little n is larger than that capital N, then the difference between a sub n and L in absolute value is less than epsilon. The L in our example would be 1.5. We're going to take this to be the definition of the symbol limit as n goes to infinity, a sub n equals L. Whether or not any of the a sub n's ever are exactly equal to L or not is irrelevant to me. Based on the numbers that we've calculated, we think that the limit as n goes to infinity of 3n plus 2 over 2n plus 4 is equal to 3 halves. Now, it's going to turn out that this is true. There are several ways to think about it, though. The first way, and the most unpleasant one, is to think of the definition. I have to look at the absolute value of an minus what I think the L is. Somehow or the other, I have to convince myself that I can make this as small as I want to make it by making the index be bigger than some particular threshold value. What follows is just some algebra. I get a common denominator, I combine the fractions. 2 times 2n plus 4 is positive since n is positive. Absolute value of negative 8 is 8. This simplifies down to 4 divided by 2n plus 4. And that simplifies down to 2 divided by n plus 2. Informally, we can see that it's going to work out for us. By making n big enough, n plus 2 will be very big. 2 divided by a very big positive number is a very small positive number. And by making the little n big enough, I can make this quantity as small as I want to make it. That's informally, though. What I really have to do if I want to convince myself that this is right is, given an epsilon bigger than 0, I have to tell you what the capital N should be. So, given an epsilon bigger than 0, for which index is little n is this going to be true? Multiply through by the positive number n plus 2, divide through by the positive number epsilon, subtract 2 from both sides, and it develops that 2 over epsilon minus 2 needs to be smaller than the index little n. Of course, 2 over epsilon minus 2 may not be a whole number. It is, however, a number on the number line. So figure out what 2 over epsilon minus 2 is, and then find a positive number to the right of that. If little n is bigger than that, then little n is bigger than that, and that capital N will do. So find an integer bigger than 2 over epsilon minus 2, and everything works out fine. The second idea that sometimes works is that I can just do some simple algebra rearrangements of the thing. In what follows, just keep in mind that n is a positive number. In particular, a positive whole number, but positive anyway. I'll factor an n out of the top and bottom and cancel it out since it isn't 0. So a sub n is actually a fraction. It's 3 plus 2 over n upstairs and 2 plus 4 over n downstairs. When I have the limit of a fraction, it's legal to split it up into the fraction of the limits only under certain circumstances. Both limits have to exist, and the one on the bottom should not be 0. As n tends to infinity, 2 over n tends to 0, and 3 plus that tends to 3, whereas 4 over n tends to 0, and 2 plus that tends to 2. The limit of the top exists, the limit of the bottom exists, the one on the bottom isn't 0, so we're in business. If a person had not paid attention during the infinity is not a number discussion, they might be thinking, well, you could have just gone straight to the thing directly. You could have just written this. I'll just take the original problem and split it up into the fraction of two limits separately, and then do those limits. When n equals infinity, 3n plus 2 must equal infinity, and so does 2n plus 4. You'll notice the red wrongs and words in various languages indicating that this isn't a good thing. In order to split the limit of a fraction up into the fraction of the limits, both limits have to exist, and the one on the bottom isn't 0. The top limit doesn't exist, which is why writing it as being equal to infinity is a terrible notation. The limit on the bottom doesn't exist either. This is no good. It's not guaranteed to be valid. Even if it was, I don't know what to do about infinity divided by infinity. Another thing you can do is called yet another variation of an f of x trick. Suppose that f of x is some ordinary nice function that you can take derivatives and limits and do L'Hopital's rule too, and all of that sort of thing. Suppose also that f is special in the sense that when I plug a positive whole number n into this f for the x, I get back a number n. Furthermore, suppose that the limit as x tends to infinity of f of x is L. If all of this stuff is true, then the limit as n tends to infinity of a sub n is L as well. It's not very hard to see why this is true. Under these circumstances, think about x equals 5, x equals 6.1, x equals 100,000, x equals 1,020,017, x equals 2.5 billion times pi, and so on and so forth. Thinking about all of these x's, as the x becomes indefinitely big, f of x gets close to L. But amongst all of these different x's, there are some x's like 6.1 and 2.5 billion times pi, which are not whole numbers, but there are also 5 and 1,020,017. Amongst all of these x's that are getting really big, you also find all the positive whole numbers that are getting really big. So if these f of x numbers settle down to something, just think about the f of x's that go with whole numbers. The f of x's have to approach L. The a sub n's have to approach L also. Returning to that same example again, I can't do L'Hopital's rule or something to it as it stands because the n makes sense not on a continuum like an interval, but only at n equal 1, 2, 3, and so on. So I'll make up an ordinary function with a variable x that can take on many different real values, and I'll think about doing L'Hopital's rule to that instead. If that limit exists, then because of what we just said a minute ago, this limit will exist and be the same number. In terms of our previous calculus work, this limit is an indeterminate form of type infinity divided by infinity. So take the derivative of 3x plus 2, take the derivative of 2x plus 4. This limit behaves in the same way that this limit does. This limit is equal to 3 halves. By L'Hopital's rule, this limit is equal to 3 halves as well. And therefore, by the f of x trick, I'll say that the limit of an as n tends to infinity must be 3 halves also. Thinking of the limit of sequences, there are various limit properties that we're used to. We're thinking that the limit of the sum of two things should be the sum of the two limits. The limit of the difference should be the difference of the two limits. Products and quotients, assuming the one on the bottom isn't 0. Have to emphasize, though, this assumes that both of these limits individually make sense. If one of them doesn't, and I write something equals something that doesn't make any sense plus something else, then I'm writing nonsense. As an example of how this logic works, suppose that the limit as n tends to infinity of an is equal to some real number L, and that the limit of the bn numbers is some real number m. Both limits exist. I want to show that the limit as n tends to infinity of the numbers an plus bn equals the limit of the an's by themselves plus the limit of the bn's by themselves. According to the definition, if you give me a number epsilon that's bigger than 0, I have to show that the difference between this and that can be made less than epsilon by making the index bigger than some particular threshold value. To somebody who hasn't thought very much about this, the knee-jerk response is to say, well, it's obvious, except that it's not obvious. It's not obvious at all. So we're going to think about this the right way. Somebody walks up to me and gives me a positive number epsilon. If epsilon is positive, epsilon over 2 is positive. The limit as n tends to infinity of an equals L means that just by making index n big enough, I can make the difference in absolute value between an and L smaller than any positive number that was previously given to me. Epsilon is positive, but epsilon over 2 is positive also. There is an index, which I'm going to call n1, so that when little n is bigger than that n1, the difference in absolute value between an and L is less than epsilon divided by 2. The limit as n tends to infinity of bn equals m means there's an index, n2, which might be the same as n1, or might be bigger than it, or might be smaller than it, so that when n is bigger than n2, the distance on the number line from bn to m is less than this positive number, epsilon over 2. So we look at the number an plus bn minus the number L plus M. I can rearrange this absolute value of an minus L plus bn minus M. Absolute values obey the triangle inequality. So this absolute value is less than or equal to absolute an minus L plus absolute bn minus M. If I choose my index to be bigger of the two numbers n1 and n2, then this inequality is true, and so is that one. So this, which equals that, which is less than or equal to that, will be less than epsilon over 2 plus epsilon over 2, which is epsilon. If n is the bigger of these two indexes, capital N1, capital N2, then this is less than that, less than epsilon, which is what I wanted to prove. The one for the an minus bn is similar. An times bn is more complicated. An divided by bn is more complicated than that, but you can provide a logical argument to convince yourself that these things are all true. To finish this first video, I want to talk about the idea that if you have a bounded monotonic sequence of numbers, then it converges. For clarity, I'm going to think of the situation where the individual an numbers are getting bigger as the index increases, and I'll call the interval that I know that they lie in alpha to beta. Now, given an interval that contains all the a numbers, it may not be the smallest interval that you could use. In particular, I'm thinking about the right end of the interval. It could be that between beta and some prior location on the x-axis, there are none of the a numbers. That could happen. If so, I'll just shrink my interval down. It could be that between my new beta and some distance to the left, there are no of these an values. This can't continue forever, though. I can't push the right-hand end of my interval too far, or I'll begin running into some of the A numbers. Out of all possible right ends, I'm going to call the smallest one capital L. L is going to be the smallest number so that all of the AI numbers are either at L's location or to the left, either here or over here. Here's the key point to the argument. Select a positive number epsilon and look at L minus epsilon on the x-axis. I've been here at L and I've just backed up a distance epsilon. I claim that there have to be some of the AI numbers between L minus epsilon and L. The reason for that's perfectly clear. If that were not true, then L minus epsilon would be an upper bound for the A numbers, smaller than the smallest upper bound of the A numbers, which is an obvious contradiction. On the other hand, the A numbers are increasing, so as I increase the index, the A numbers on the x-axis move to the right. All of them are smaller than L, and all of them are within distance epsilon of L. Cleaning the language up. Given epsilon bigger than 0, there's a capital N, so that if little n is bigger than capital N, then the absolute value of AN minus L is less than epsilon. That, see, is the formal definition of the statement limit as n tends to infinity, AN equals L. You can make similar arguments if the sequence is decreasing. You can make similar arguments if it's increasing, then holds constant value for a while, and then increases again. But as long as you have a monotonic bounded sequence, you're guaranteed that it converges. This is all I wanted to talk about in Rambling Calculus video number 1. I hope you're having a good day. I'll talk to you again soon.